Hello everyone. So it's a great pleasure to have Dr. Wei Zhu from Georgia Tech to give a talk at our One Word Mind seminars. So Dr. Zhu is graduated from UCLA, so he's my academic brother, so I'm pretty proud of. And he's now currently assistant professor of School of Mathematics at Georgia Tech. His research is lies in the intersection of applied math, machine learning, with a focus of mathematical foundations of machine learning and applications in scientific computing and computer visions. So today he will talk about structure preserving machine learnings and data-driven structure discoveries. Yeah, please take it away.
Thank you. Thank you, Siti. Well, I'm very proud of you as well, as you know. And yeah, this is actually my second time being invited to Minds. The first time was 2 years ago. I talked about something along this line of research. Today, I'm going to talk about something a little bit different, some new results that I want to report, but I might have set my stage a bit too large. So as I was preparing the slides, I think I'll probably most focus on this first part on the structure preserving genuine models. And then, if time permits, I'll go to a flip side of the coin and figure out how to use data-driven methods or machine learning model to discover structure data from data. Okay, so let's begin. So the first part of the talk is based primarily on a sequence of wonderful collaborations with my former colleagues and friends at UMass. In particular, I want to highlight Dr. Ziyu Chen. He was a VAP at UMass, working with me and my colleagues, Marcos Katsoulakis and Luca Rigolet. And he's pushing a lot of boundaries of what we have been exploring, and he will be joining UNC Chapel Hill as assistant professor in the fall. Okay. So I want to talk about generative model, but I guess for the audience, it's not necessary actually to explain the background, but let me just very briefly cover some of the necessary terminology. It's probably not necessary, but anyway. So you have seen a lot of applications of generative model, and you've definitely seen this kind of applications where you have given a bunch of real images, and the task is to find a mechanism to generate fake images that look very much similar to the real given data. And mathematically, what does that mean? It means you have a bunch of samples, x1 from all the way to xm, coming from some unknown target distribution Q. And this Q is typically, say, supported on some low-dimensional manifold, but you don't have access to Q, but samples from Q. And generative modeling is trying to learn a mechanism to generate new samples, say Y1 to In, coming from some generated distribution PG. And what you want to achieve is that you want this PG to be very close to Q. Okay, so now the question is how to achieve this. Well, I'll explain to start how this is achieved in generative adversarial networks, or GAN for short. And gradually, as we progress, we will talk about the diffusion model as well. But here, this is just some basic illustration of how generative model is achieved to produce generated samples. So here, GAN, it is essentially a two-player game for learning an unknown target distribution Q. And there are two players in the game. And what is the first player? Well, the first player is called a generator. This is usually a neural network, and the role of the generator is to, well, it generates the samples. And how to achieve this is that you first specify some prior distribution, say the Gaussian distribution or any distribution that is easy to sample from. And then the generator is a neural network or some map that maps a input random vector to a output signal or output image. So essentially, this generated distribution PG is nothing but the push forward of the prior distribution PZ under the generated network. Okay, so now you have a generated distribution. How do you make sure these two distributions, PG and Q, the ground truth target, are very close to each other? This is where the second player, the discriminator, comes in. And the role of the discriminator is to make sure these two are close. And how this is achieved? Well, the way to achieve this is first, the discriminator is a function that maps a sample, a real or fake, into a number. And then you build some discrepancy function h with respect to both the discriminator and the two distributions that you want to tell the difference. And the one example is the mean discrepancy, which is defined as the difference of the expectation of some discriminator gamma with respect to the two distribution. For example, say if in the beginning your generator is pretty crappy, meaning that you are producing very crappy images. So these two distributions should have very dissimilar support. They should be very different from each other. In this case, you can choose a good discriminator such that it assign high values to sample from Q. So you have a large mean with respect to Q, and assign low values to sample from P. So this is small, meaning that the discrepancy here is large. So intuitively, what this means is that the role of the discriminator is trying to tell whether an image is real or fake, whether it's coming from Q or whether it's coming from PG. Okay, so once you have this discrepancy function, then you can define a probability divergence between two distributions, which is the maximum discrepancy as told by all discriminator gamma within some function class that is specified, capital gamma. Okay, so for example, the Wasserstein-1 distance is defined by choosing this gamma, this capital gamma, to be Lipschitz-1 functions on the space X. And the H is indeed defined, in this case, the mean discrepancy. Okay, so probability divergence can be viewed as a notion of distance between two distributions defined by the discriminators. Okay, so once you have this, then indeed GAN is a two-player game trying to minimize the distance between the target distribution Q and your generated distribution PG by choosing a good generator. And this distance, as I repeat, is defined as the maximum discrepancy as told by all discriminators within some function class capital gamma. Okay, so this is some general setup. And one problem with GAN, well, GAN has produced very good results, but one problem with GAN is that you still require a huge amount of data to generalize well. And to align with the theme of today's talk, we want to somewhat reduce the data requirement of GAN such that it can perform well even if you don't have that many data. And one way to achieve this is to leverage the intrinsic structure of the data distribution. And indeed, many real-world data will have intrinsic structure. For example, if you're looking at medical images that are taken without orientation preference, then this distribution that you want to generate, this Q, should be rotation invariant. So what this means is that an image and its rotated copy should have the same likelihood, or they are equiprobable. So what this means is that, again, an image and its rotated copy should have the same probability, and the distribution Q you want to learn, you want to generate images from Q, this Q should have group symmetry. It is invariant under rotation. Okay, so now the first part of the talk will be following under the following few topics. That is, first, how can we impose structure, a particular symmetry in generative models or GANs, such that you can improve the data efficiency. And second, once you impose this type of structure in your GAN, how do you quantify the performance gain in terms of how many fewer samples are actually required once you put more structure into a modeling process. And lastly, I want to generalize the framework into not just the diffusion, not just the GAN, but also diffusion model, and also flexibly impose general structure, not just the group symmetry, but also cater to, say, multimodality, low dimensionality, or approximate group symmetry. Okay, so this will be the topic of the first part of the talk. If I have time, I'll go to another flip side of the coin. Okay, so first let's go to the first subtopic, that is how can we impose symmetry in GAN. Actually, 2 years ago, I talked about this in the MINDS seminar, so I'll briefly explain how this is done. Okay, so we have the same GAN framework. Here we want to learn the target distribution Q, but this time we have an extra information that Q is invariant to some group sigma. I call the group sigma because I've reserved the generator G to the generator space. Okay, so the target distribution Q is invariant to a group sigma, and the question is how to incorporate such structure, the group structure, into the two players, the generator and the discriminator gamma. Okay, so first, for the first player, the idea is very simple. Let's focus on what you can do to the generator. And the role of the generator is to generate a distribution. And because we know the target distribution Q you want to generate is invariant to the group, that means, well, you only need to generate distributions that are invariant to the group as well. And this can be easily achieved by specifying a good prior distribution and build your generator to be uh, nice to preserve the symmetry. So what you can do is that you first specify some prior distribution PZ, so this noise distribution that is invariant to the group sigma, and then you build your generator G to be equivariant to the group. And equivariant, essentially what this means is that if you, well, perform some group action on the input, say the noise vector, you want the same or similar group action to be applied automatically to the output. One example, if the input is rotated, you want the output to be rotated as well. You can very easily show that if the prior distribution is invariant and the map is equivariant, then the generated distribution is going to be invariant to the group as well. So what this means is that the symmetry information of Q can be easily built into a smarter generator and by choosing a good noise source. Okay, so this is not that interesting. Now let's look at the second part, the discriminator story, and how to build a smarter discriminator. Well, because now we have generated distribution PG that is invariant to the group, and we also know that the target distribution Q is invariant to the group, meaning that the realness or fakeness of an image remains the same after some group action. So what this suggests is that the discriminator, whose role is to tell the difference between a real and fake image, should be built to be invariant to the group. The realness and the fakeness should remain the same after some group action. Okay, so to put this intuition into more rigorous statement, what this means is that if you have two distribution P and Q that are both invariant to the group, then the divergence between two distributions, which is the distance, as defined by gamma, again, I repeat, it's the maximum discrepancy as told by all discriminator within some function class capital gamma, is the same as this quantity, which is taking the maximum with respect to all discriminators that are invariant functions. So this gamma sigma is the subset of gamma that includes only sigma invariant smarter discriminators. So when you tell the difference between two distributions, you only need to look at invariant discriminators. And what this means is that we only need to optimize over the smaller subset of sigma invariant discriminator to compute the divergence. Okay, I'll come back to this again to explain why this gives you better result. But here, everything is very intuitive. Okay, now let's see. Once you have built a smarter players, what you can do. So this is some experiments on generating rotated MNIST digits using only 1% of the training data. So here we only have 600 images. And the digits are rotated randomly and uniformly across the group orbit or SO2. So as you can see, the left panel shows the result when you have ignorant players in the game, so meaning that both discriminator and generator are just a generic neural network. And if you just replace that with invariant and equivariant networks, you will have significantly improved the results in the sense that you have higher quality digits generated, but also more diverse rotation along the group orbit. And you have similar story when you deal with somewhat real data sets. So NHIR, which is a data set of pathology slides, indeed, it is invariant to, say, rotation and also flipping. And if you're an ignorant player, you'll see that you have a lot of artifacts in the generated images here and here and there, and those can be cleaned up if you have a smarter player in the game. Okay, so this gives you some intuition and also some empirical evidence on why symmetry after building into your generative model can help you generate better images, better samples, or alleviating the data requirement. Okay, so now let's move on to the second topic, that is how can we quantify the performance gain? That is exactly how many fewer samples are actually required. Okay, so there are many reasons that are potentially behind this performance improvement. Some of them are somewhat intractable due to training aspect. I will touch upon in a moment. But I would say that the most important reason behind this improvement is coming from the smarter discriminator theorem, which recall is that if you have two distributions P and Q that are both invariant to the group sigma, then to tell the difference between two distribution or the distance between two distribution can be told by sigma invariant functions. That is a smaller subclass of gamma. And this reduction from the original function space, the discriminator space, to invariant discriminators can provide a better empirical estimation of the divergence between two distributions. Okay, so what do I mean by saying this? Let's recall again. The divergence between two distributions is the maximum discrepancy as told by all discriminators within the function class capital gamma. This is a well-defined quantity, but it is not really computable because you don't really know what Q and P are. You only usually have finite samples from Q and P. And to estimate what this quantity is, you can only use finite samples coming from this distribution. Say if you have x1 to xn coming from the that are samples from P, and yn to yn are samples from Q, then you can replace P and Q by their empirical measures supported only on the sample, and use this quantity to approximate the divergence that is not accessible to you. You don't have closed formula for P and Q. Okay, so by our smarter discriminator theorem, what we know is that if Q and P are both invariant to the group, then we can potentially have a better estimation. That is, we can replace this gamma by the sigma invariant subclass of discriminators. And we use this quantity to estimate what the divergence is. Okay, so this should potentially be an improved estimation. And now the question is, how much more accurate is the new estimation? Right. The answer to this question is very much nuanced. It depends on the group action. It also depends on what type of divergence you're looking at. For this talk, I will be only looking at the maximum mean discrepancy, or MMD for short, which is indeed defined as the maximum mean discrepancy. So this is the mean discrepancy with respect to the discriminated space gamma. And this gamma is the unit board in some reproducing cumulative Hilbert space, actually with some defining kernel function kxy. So fairly certain the audience are very familiar with RKHS, but if you're not familiar with RKHS, you can just think of it as a Hilbert function, a Hilbert space of nice functions. Okay, so we have a MMD, which is the distance between two distributions, and the estimator that we can build that take into account the symmetry of the group sigma to estimate the divergence between P and Q. So we estimate this divergence between the MMD between Q and P using this estimator. We're using finite samples Qn and Pn, and we are only looking at discriminators within this invariant function space. Okay, so here's the result that quantifies the estimation error. So assume that you have a finite group sigma acting on the space X, and you have two distributions P and Q that are both invariant to the group sigma. Then with high probability, your estimation error can be bounded by the right-hand side. So on the right-hand side, this M and N are the number of samples coming from Q and P. And this capital A sigma K is a number that depends on both the group sigma and K, which is the kernel. So this capital A in turn can be written as some square root of little a sigma K, which is a number depends also on sigma K and in between 0 and 1. And this absolute value of sigma denotes the size of the group. Okay, so this formula, we can write down the closed form formula for this. I see there is a question. No absolute value in the definition of MMD. Well, because this is a symmetric space, so you can take a negative gamma, then you have the negative of that guy. So supremum of that guy should be always positive.
Okay, thank you.
Yeah. Thank you. Okay, so this little a is something that we can write down, but it's going to be not that intuitive. But let me try to intuitively explain what this result means. Okay, so let's assume. So first, a is a number that should depend on both sigma and k. It is in between 0 and 1. Now let's first assume that this thing doesn't change as sigma changes, and it stays always close to 0. If this is the case, then this capital A is going to be staying close to 1 over sigma absolute value, 1 over square root of the sigma. And if we plug this into the previous formula, then this divergence estimation should have an error that is bounded by 1 over sigma times m square root. Okay, so this result is fairly intuitive. So what this means is that to achieve the same level of the right-hand side, if you want to set the right-hand side to be epsilon, After taking into account sigma, the size of the group, then instead of using m samples, you only need m over sigma samples. So what this suggests is that to achieve the same level of accuracy of the same level of error, the number of samples required is reduced by a factor of sigma, the size of the group. Okay, so this is very intuitive, but now let's see what would happen if this little a is very close to 1. If this little a is close to 1, then this capital A is going to be close to 1 too as well. And to plug this into the previous formula, this becomes something that doesn't depend on sigma at all. Okay, so what this suggests is that no matter how hard you try to put the sigma information into your estimation, you do not have any gain in your estimation. Okay, so in reality, the situation is a bit more interesting because this little a will change as sigma changes. In an example I will show later on, this little a in the beginning will stay very close to 0, meaning that as you gradually increase the size of sigma, the estimation becomes better and better. But at some point, this a will jump very close to 1. And after that jump, no matter how hard you try, there is no way for you to further improve the estimation. Okay, so the example I was alluding to is when you have two distributions P and Q that are the same. They are both a mixture of 64 Gaussians. And for this reason, they are sigma invariant, where this group sigma can be C1, C4, C16, C64, where CK is the discrete rotation group with K angles. So C1 is the rotation by 1 angle, so there is essentially no group symmetry, or it's a trivial group. And C4 is the rotation by 4 angles or 90 degrees, and C16, C64, etc. Okay, so now we also look at the kernel function. We're looking at MMD. So the kernel that defines the MMD are always Gaussian, but we look at the different Gaussian kernels with different changing bandwidth. So when S is large, you have a larger bandwidth, meaning that the kernel is decaying slowly. If S is small, then kernel is decaying faster. Okay, so now our question is the estimation getting more and more accurate with a fixed kernel as you gradually increase the size of the group? Okay, so now let's look at the first one, the result in the first panel where the kernel S is chosen to be relatively large. So this is when the kernel decays slowly. And the horizontal axis shows the number of samples, which is in the role of M and N in the estimation. And the vertical axis shows the computing the divergence between the two distributions. So it's the estimation error. So as you can see, as M and N increase, of course, the estimation becomes better and better. And different color shows the result when you're changing the size of the group, goes from 1 to 4 to 16 to 64. And you can see there is a significant separation of curve between sigma equal to 1, which is the blue one, and sigma equal to 4, which is the orange or red one. And after sigma equal to 4, there is no significant increase anymore. All the curves for sigma 4, 16, 64 are mingled together. Okay, so what this means is you have a significant improvement in the beginning, but in the end, after sigma equal to 4, it doesn't improve any further. And the reason why this happened is, as I explained before, this little a in the beginning stay close very to 0, and when sigma becomes 4, suddenly it will jump to too close to 1, and after that jump, no matter how hard you tried, you can put more information into your estimation, you do not have any additional gain. And this was what happened if you change the kernel bandwidth to be smaller. In this case, you change the bandwidth, so you change a different version of MMD defined by different kernel. In this case, you have an extra separation of curve between sigma equal to 4 and 16. So what this suggests is that you can further improve, or you have more way to squeeze out your estimation improvement. And the reason why this happened is because in this case, this little a stays close to 0 a little bit longer. It will jump when sigma is equal to 16 instead of 4. And if you further decrease the bandwidth of the kernel, then you have extra separation of curve. Okay, so take-home story of this result is essentially saying that, well, empirically, indeed, you will see that putting more information of or more structure of the target task into your estimation, the result can become better and better, but there could be some plateau. after some threshold, in this case, no matter how hard you try, you will not squeeze out any additional gain. Okay, of course, this only tells a very small part of the story in the generative model, where we only look at the discriminated part, the divergence estimation. So that is essentially trying to tell the difference between two distributions. And we have two follow-up works. Well, one is not follow-up, but the first work actually takes into account the entire story, where you have the generator and the discriminator, and also we take into account the approximation into the entire picture that quantify rigorously the statistical guarantee or gain of group invariant gains. And the second part is not really related to the generative model, but actually take into account the training aspect where you have a structure preserving or equivariant steerable networks to do a binary classification, because in the end, when you try to minimize or to tell the difference, do the divergence estimation, it's kind of like a binary classification task. So the second piece of work we look at what's the solution that actually equivariant model are converging to. Is it really better compared to the generic counterpart? Okay, so now let's move a little bit from GANs to somewhat more general models, say diffusion models. And also we want to generalize the concept to general structure, not just symmetry anymore. Okay, so first, what are diffusion models? This should be pretty familiar to the audience as well. But let me just briefly explain. The diffusion model is essentially a pair of stochastic differential equation, SDE, where the forward SDE is a user-prescribed diffusion process. So user prescribe what F is, what G is. And this forward SDE will take a data distribution, X naught, a sample from the data distribution to XT. That is essentially some purely noise. Depending on how you choose this F and G, will converge to, say, some noise distribution. And how you generate your data is coming from the reverse SDE. And the reverse SDE will send a noise from some prior distribution, which is the invariant distribution in the forward process. And it will gradually send your noise through this reverse SDE to the target distribution that you want to generate. And the core in the diffusion model is the score function, which is defined as the gradient of log density of the marginal log density of any time t distribution at x. And this is usually not accessible. And the diffusion model, the key aspect of the diffusion model is to approximate using a neural network what this score function should be. And well, now let's say we can think about the previous framework again. Now let's assume that the distribution P that you want to generate, the data distribution, say it's exactly invariant to a group. And now say if you design the full process to be nice enough, say if this F is a if it's an OU process, or it has it's a unitary action on X, then in this case, you can prove that at each time step, the marginal distribution PT should be invariant to the group as well, meaning that log of PT should be invariant function. And now if the group you're looking at is a unitary group, then this gradient of log of an invariant function should be an equivariant vector field, meaning that you only need to approximate the score function using some equivariant neural network at each time t. Okay, so meaning that, well, if you know the exact structure of your input, you can build this exact group symmetry into the score function if the input action is unitary. However, the problem that it is somewhat rigid. It can only deal with, say, exact group symmetry if you want to enforce it into the learning of the score function. Another way to achieve this is not putting your information into the score function, but instead we put our information of your input or target distribution into the reference bit distribution, which is the one that gradually diffuse through the forward process. And indeed, what we can do is that we can build our reference distribution to have structure that resemble the target. And these type of structure could be multimodality, approximate group symmetry, no longer exact group symmetry anymore. And it can also be low dimensionality. And the key aspect is that you want to build a distribution that is first tractable, so that it's easy to sample noise from distribution. And second, it should be close or resemble what the prior distribution should be. And one problem is that you would require some design nonlinear drift function f and special training, because this time we want to not just diffuse to say Gaussian noise, so you cannot always choose f to be a linear function, which is usually the case. If f is linear, you have an OU process, everything converges to noise. That is standard Gaussian. But now we want to choose a different reference. You might require choosing a different score, choosing a different drift. Okay, so now let's see, if you build your information into reference, what do we need to modify? So first, let's recall the key aspect in training a diffusion model is to match the score, or the score matching, which is usually done by denoising score matching. And the key in denoising score matching is that you will need to sample input x naught, and for each time t, you need to sample from the conditional probability of xt. And the key aspect is that you need to know what is the transition probability from time 0 to time t of x naught, xt condition on x naught. And if f is a linear function of x or affine function of x, then the condition probability p t given 0 is always having a closed form formula, because it's essentially a Gaussian distribution. So for OU process, everything is very simple. You can know what is x naught, you can sample xt, and this has closed form formula. And now let's say this is no longer an OU process. Say xt, the final distribution, the one that resembled the prior, is a multimodal distribution with each mode resembling the mode of the input. And in this case, you cannot design a forward process that is OU, because everything will be Gaussian. But instead, you might want to build your forward process to be some longevity dynamics designed to match different mode. In this case, you can have a nonlinear process. If it's a nonlinear process, the transition probability from time 0 to any t is not known. So how can you do that? Well, so if this is the case, then the idea is fairly simple. Even though you do not know the transition probability from 0 to any t, but for adjacent t, if you have a small delta t, then if you choose a delta t very small, then the condition probability of pt plus delta t condition on t should be approximately Gaussian. And then you can use this information that the transition probability is approximately Gaussian between adjacent delta t time to match the score. Of course, you do that, you will come across some numerical issue, that is, you have a small delta t, then actually you have a variance exploding term. And this can be fixed by some simple numerical analysis or some control variable to remove the mean zero term and control the variance. But anyway, once you have designed all the process, please refer to our paper how this is done. But once you can do everything, then you will have some significant benefits. And here is an example when we want to say learn the target distribution. So this is a baby example. This is the true samples. And if you use OU process plus explicit or the denoising score matching, this is typically done in diffusion model. As you can see, the generated samples are somewhat blurry and it doesn't really match the input. But if you use a Gaussian mixture as the reference distribution, that is somewhat learned from the true samples, and then you use a forward process, that is the longevity dynamics, then you'll see that, and also using nonlinear denoising score matching, then the generated samples will be much better. And similarly, we can take into account, say, for more realistic data set. So this is MNIST digits, still pretty fake. But if you run OU plus DSM, so that is the generic model, OU process with denoising score matching, you'll see that generated digits, even though they look pretty realistic, there is some problem. That is, if you look at different samples, the fraction of samples generated, you'll see that the digit 1 is generated very often, almost 30%, more than 30% of the time. So meaning that the denoising, well, the generic model is actually favoring this specific mode digit 1, which is easy to sample. But now if you fix it by, say, choosing a Gaussian mixture as a reference distribution and do nonlinear denoising score matching, you'll see that the digits sampled have similar quality, but the number of the digits generated in each class or each mode is much more balanced. Okay, and it can also deal with not just multimodal, but say approximate group symmetry. This time it's not exact group symmetry. And here what we do is that we say you have originally upright large digits, and then we can also randomly flip the digits, but at each time we flip, the digits should be shrinked. So meaning that you have a distribution that is approximately C2. All the digits that are large should be upright, all the digits that are small should be flipped. And then this has some approximate C2 symmetry. We want to see if you use, say, our model, is it going to generate this distribution better? Okay, so this is the result when you just use generic model. And then again, OU plus DSM, then here we keep track of the fraction of samples that are generated using the generic model. As you can see, the model is mostly generating small digits, again, digits that are easy to generate. And if you do, say, we're not putting information into the reference bit distribution, but we put exact score symmetry information into the score. So we parameterize the score function as a equivariant neural network, then we see that you have some problem. That is, you're not really learning the original distribution, but instead you're learning a symmetrized distribution. Because here, as I recall, all the large digits should be upright and small digits should be flipped. But here we will see that small digits that are upright, the large digits that are flipped. Meaning that if your underlying distribution is not exactly group symmetric, you parameterize your score function to be exactly equivariant will cause problem by learning a symmetrized version of the original distribution. But this can be somewhat fixed up if you use a Gaussian mixture as the reference distribution and see that the samples are much more balanced. Okay, so maybe I have 10 more minutes. So I will shift the gear a little bit. So previously we talked about how to incorporate the structure of your learning task into your model. And after taking into account the structure into model, what kind of performance gain you can achieve. And now let's look at the flip side of the coin. Let's say you have a bunch of data. How do you discover structure from your data? And this structure can come in the form as, say, discover a conservation law or a bunch or the exact number of conservation laws of data coming from, say, a dynamical system, or how do you discover the structure that is a moment closure model or lax pair or integrability of the system. There are a few references that I'll put it here, but let me just maybe, due to time constraint, I'll only focus on one thing. That is, how can we discover a maximum set of conservation laws from a dynamic system? So here is a little bit of background. Let's say you have a d-dimensional dynamical system, that is dx dt is equal to fx. So f is some vector field on Rd. So this is essentially ODE. And what is a conservation law of a dynamical system? Conservation law is essentially a function on the state space that remains the same or remain constant over all trajectories governed by this dynamical system. That is, if x is governed by this ODE, then I of xt, so the quantity at each time, all the time should remains the same. So I is called a conserved quantity for this dynamical system. A simple example is when you have a spring mass system. So you have a harmonic oscillator given by x, the state space is a pair of q and p. And here the energy is conserved, that is, but the potential energy plus the kinetic energy is always the same as t goes on. Okay, so now the question is, well, if we're given a Hamiltonian system like this, you have extensive knowledge of what the system is modeling, so you know that the energy should be conserved. But now let's assume that you do not have any prior knowledge of the system. You're just given the ODE, or even worse, you're just given some trajectory samples from this ODE. How do you know, or how do you discover conservation laws from data? And the second question is even more ambitious. That is, how do you discover all of them? So we can given a system, how to discover all conservation laws from this dynamical system. All right, so first, what do I mean by discover all of them? Let's assume that we are looking at a d-dimensional Hamiltonian system. Let's assume that it's also in the canonical coordinates. So you have a position q and the conjugate momenta p, and this there is a function h that is called a Hamiltonian, and this function, the vector field f, is defined as this gradient p of h and negative gradient q of h. And we can also define for the Hamiltonian system a Poisson bracket between two functions. Say if you have two functions, say two conservation laws, then the Poisson bracket between these two functions is defined in this way. And essentially, it's just the gradient of I, gradient of j in the middle, gradient of I times gradient of j in the middle. There is a symplectic matrix. Okay, so this is when this is the Poisson bracket, and if you have a collection of conservation laws from a Hamiltonian system, then this collection of conservation laws is called a functionally independent, meaning that at each point x in the state space, the gradient is a collection of independent vectors. Okay, so what this really means is that there is no way for you to nonlinearly combine this collection of conservation law to give you zero function. So they are nonlinearly or functionally independent. And we also say this collection of conservation law to be Poisson commuting or in involution if the pairwise Poisson bracket is equal to zero. Okay, so for a d-dimensional system, what I mean is that the state space is d-dimensional, or this Q is in RD half, P is in RD half. There should be at most d half independent conservation laws in involution. So this is what we know. Given d-dimensional dynamical Hamiltonian system, there are at most d half independent conservation laws in involution. And if such conservation law exists, then this system is called integrable or fully integrable in the Liouville sense. Okay, so what we know is that there should be at most a d half. And now the question is, given some generic Hamiltonian system, how we exactly pinpoint how many conservation laws are there without extensive knowledge of this Hamiltonian system. And if you don't know this exact number, how do you discover them altogether? Okay, the way that we achieve this, also what we're going to explain is fairly computational. So there is not that many theory. There is a fake theorem in the next slide, but it's purely computational, and there's some idea that borrows from the idea of deflation methods for computing steady state PDE. So this is what we coined the neural deflation method. And the intuition is that we want to learn conservation laws one by one. After you learn a collection, to learn the next one, you want to maintain functional independence and involution between the previous one. And the idea is you first learn the first conservation law just by the definition. I want to parameterize your I1, the first conservation law, using some, say, neural network or whatever ansatz you want to provide. I want to train it such that the direction field in your system, in your dynamical system, is always orthogonal to the gradient of the quantity that you parameterize. Essentially, what this says is that you parameterize a quantity that is conserved along trajectory of the dynamical system. This is fairly simple. And now, once you have learned a collection, so this is a inductive statement. Once you have already learned the collection of conservation law, to train the next one, what you do is that you build a loss function using the following way. So the first part of the loss is essentially saying, well, when I'm learning the case conservation law or case quantity, I want it to be conservation law. So this is the conservation loss. And this part is ensuring that the case quantity that you learn is indeed in involution with the previous one. So this is also intuitive. This is the involution loss. And what's interesting is the denominator. And the denominator is the so-called deflation loss coming from the deflation method. And the deflation loss is imposed in such a way that it will create a pole at each point x, the subspace that is spanned by the previous learned conservation laws. So what it can achieve is that when you learn the next conservation law ik, you will push anything that is away from the span of the previous conservation laws at each point x. Okay, so this alpha is some strength of the deflation, essentially how large this pole should be, how strong the pole should be, such that it will be pushed away from that. Okay, so we have, as I said, a fake theorem that essentially says that this loss is somewhat well posed. No, it's a consistent in the sense that if you have some probability measure on the state space, and if you replace every point as a finite sum by the expectation, then at least if all the conservation laws you learned previously is exact, then this loss is equal to 0 for the currently learned conservation law, if and only if this combined set of the current conservation law that you're learning and the previously learned conservation law is indeed a K-independent quantum-commuting conservation laws. Okay, so there's some theoretical justification, but now let's just take a simple look at some very simple settings. So you have a 2D harmonic oscillators. In this case, it's just a 1D harmonic oscillator expanded by by a y direction. So you have Q1, Q2, P1, P2, and the Hamiltonian is given as such. And this is fully integrable. We know that there should be two independent conservation laws. And now if we try to learn those conservation laws one by one, while choosing different alpha, which is the strength of the deflation, we'll see that when we learn the first one and the second one, the loss is very small. It's close to 10 to the negative 4. And we try to learn the third one and the fourth one, depending on how you choose the strength of deflation, you have a significant jump in the final loss function reported, the validation error reported, meaning that this is a fairly sharp justification saying that, well, the conservation law will stop at 2. We were able to discover 2 conservation laws, while discovering the third conservation law, it will fail. Okay, let's look at some other examples. Say, if you look at the Hamiltonian lattice system, these are all defined using the following quantity, the Hamiltonian. So this is a kinetic energy plus some potential energy, and you have n identical nodes. So this means that the Hamiltonian system is 2n dimensional, and the degree of freedom is n. By defining different potential, you have a different system, the total lattice FPUT system, Sine-Gordon, Calogero-Moses system. So you don't have to know all the exact definition, but for now, you just need to remember the total lattice and FPUT are very close to each other, closely related. So this total is fully integrable, FPUT is not. Sine-Gordon is not integrable, and the Calogero-Moses system is fully integrable. Fully integrable, again, means that the number of conservation laws should be equal to n, which is d half. Okay, so let's look at first the experiment on total. Sorry, it's not total, it's total. Total versus FPUT. Again, total is fully integrable, but FPUT is not. As you can see, if we choose the number of sites n is equal to 5, when learning total, you'll see that the fully integrable system, the loss stays very close to 0 or very small when all the way to 5, and suddenly at 6 it jumps, meaning that the method or the algorithm is able to detect the 5 conservation laws, and the 6th, when trying to learn the 6th one, it throw up the hand and said, well, this is not something I can do. But if you're learning FPUT, it jumps at the first one and then it stays close and there is a second jump. This is not something we quite understand yet, but you see that there's a sharp difference between those two. This is not a really sharp result because FPUT is supposed to have 2 conservation laws, but here it only identifies 1. But anyway, it shows a stark difference between these two systems. And now if we increase the number of degree of freedom by 1, in this case, you'll see that for total system, we can again learn 6, which is matching the degree of freedom. And for FPUT, again, it is quite different from an integrable system. And now let's look at what you can do for Sine-Gordon and Calogero. Again, Calogero is fully integrable, but Sine-Gordon is not. And if you're learning Calogero, it stays very close to 5 when the number of sites is 5. It stays very close to 0. But for Sine-Gordon, when learning the first one, it already jumped. In this case, indeed, the Sine-Gordon has only 1 conservation law that is independent. If you look at, say, n equal to 6, again, Calogero is learning all the way up to 6 and jump at 7. And for Sine-Gordon, it learns the first one and then jump and says, oh, I only have 1 conservation law. Okay, I don't think I have that much time, but I just want to briefly mention that, well, you can extend this framework to not, well, previously I'm assuming that you have the right-hand side of the ODE, but now you can also extend it to say, well, I don't have the ODE, but I actually have trajectory sampled from the ODE. And also, this type of idea can be extended to learning or discover lax pair from the system, which in turn also decide whether the system is integrable or not, depending on whether or not you can learn the lax pair of the network system. I'm happy to explain more about the detail. This is I want to mention that this is a collaboration with Jimmy Alejandro and also Pans. And Jimmy is the one, he's at ASU, and he's the one did all the hard work. Okay, I guess that's everything I want to talk about. Thank you. Thank you for listening.